Hi, you're about to watch a recording of a talk that I gave yesterday at the Department of Computer Science at the University of Copenhagen. And that talk had some problem with the sound in the first roughly 11 minutes or so. So I added another video here at the front explaining very quickly what was going on the first slides. And then I'll cut directly into the part where there is a sound again. So I'll just start with the slides. The following talk, even though it was at the Department of Computer Science, it's mostly about some theoretical aspect related to sub-Riemannian geometry and geometry in general. So two typical questions that you want to consider on such kinds of spaces is when are two spaces different? How do you know if one space is the same as another space and not just written differently? And in particular, this is important for spaces that have so many dimensions that we are not able to physically represent them. May draw a picture or anything. How can we still know if they're the same or are the difference? And what are good spaces to compare with? What do we want to consider if we want to build some intuition for the things we cannot see? So the idea of this talk is to explain how to do that in sub-Riemannian geometry. And in order to do that, I'll first answer these questions in Riemannian geometry, some very basic terms, and then generalize the sub-Riemannian geometry. So what I'm going to be talking about will be based on the following papers here. So I'll get to these results when I come to the sub-Riemannian part, the first Riemannian introduction. And I will go a little bit quick compared to what I did in the talk. And then you can find these slides on the webpage if you find that it's going too quick for you. So basically what we're going to do is we're going to look at Riemannian geometry first what it is, secondly, how do we see difference between two spaces, and what are the model spaces in Riemannian geometry. And for sub-Riemannian geometry, it would then do the same quick introduction, something about we're going to talk about what are models, and we're going to use isometry to have some sense of what models are in this setting, one or at least one approach to models. And then we're going to talk about how to see the difference between sub-Riemannian manifolds. So we can quickly think of Riemannian manifolds as going from clay shapes to paper shapes. So this folded sheet here is the same as this sheet here, because I can, if they were made of paper, I could fold it back out, whereas I cannot, if I have a paper sphere, I can press it to become an ellipsoid without tearing it. And so the equivalence class in Riemannian, the equivalence map in Riemannian geometry is called an isometry, which is a map that preserves all lengths. Riemannian geometry is named after Bertrand Riemann and his idea of representing the different kinds of shapes as an inner product on each tangent space. So we have a way of evaluating length of all things, vectors that are tangent to our manifold. And then we're also, and we can then use this to define lengths of curves, because we can evaluate the length of the tangent vectors. And using this, we can define a distance by taking the smallest curve possible. I'm just going to skip a slide here for briefness, and you can look at these afterwards. How do we see a difference between Riemannian manifolds? So this is a kind of something that's easily missed when you're learning Riemannian geometry, is that, okay, let's take the simplest space possible, R2, with the standard Euclidean metric. And then you can have a general metric on R2, which will then be written in a different way. So we can have some examples of how to put different kinds of metric on R2, which they represent different kinds of shapes. So this metric over here represents, again, this folded paper over here. Here we have a saddle saddle like this, represented by this Riemannian metric here on R2. And we can even make a sphere without the North Pole by taking the plane and using the metric like this. And so the question is now, how do we, okay, we see that all of these metrics are written differently than the standard Euclidean metric in the beginning. But are they actually different? Or could I have done a change of variable to make them look the same? And this is the same as finding an isometry. And the answer is that this one is the same as the Euclidean space, because again, the paper, you can fold down the paper. These two others you cannot make flat no matter what you do, but it's difficult to prove this by just saying that you couldn't find a change of variable to make it happen. And same, this one is a very complicated metric tensor that you can actually see, do a change of variable and see that this gives you just a standard Euclidean space. But since there are infinitely many changes of variables, how do you know if something is actually the Euclidean space or not? If two spaces, in general, how do you know if two Riemannian manifolds are the same or if they're just written differently? So the typically invariant we look at is curvature. So for Riemannian manifolds, we have the Levi-Civita connection, which gives us a way of differentiating vector fields. We can then use this to define curvature, both the curvature tensor and the sectional curvature, which I'm denoting by K. And then in a Riemannian manifold, we can check if something is actually the Euclidean space by checking this, all of these sectional curvatures and saying that they vanish, or just checking the curvature tensor and seeing that they vanish. And the important tools that we have is that we can choose one unique connection. So we have something that is independent of the choice of coordinates you get. You can have this derivative, this way of doing partial derivatives of vector field called a connection. And this allows you to set up the conditions for curvature vanishing afterwards. And we're going to apply the same sort of approach in sub-Riemannian geometry, where the difficulty becomes in this normalizing what a connection would be. Then for model spaces, what we consider the models in the setting are exactly the ones that have constant sectional curvature. So that means that this is constant no matter which plane you're using, plane sigma you're choosing. And if you have constant sectional curvature, then up to scaling, there's only three options. There's Rn, there's a sphere, and there's the hyperbolic space. And we're going to see that in sub-Riemannian geometry, there are several more options. And what I mean by scaling is the multipliable constant, which here then changes the metric tensor G by lambda square, because that will change the distance by right lambda. So this is can be difficult to generalize to the sub-Riemannian setting, because we don't necessarily know what the sectional curvature is. But what we do know is we have this alternative way of looking at what a model space is, and to say that a model space, so the sphere, the hyperbolic space, and Rn, these are the unique spaces that satisfy that it looks the same anywhere you are and in any direction you look. That means that, okay, and you can take any pair of points and you can take any isometry between their tangent space, and then there always exists an isometry of the entire manifold, which takes x to y and maps the tangent space exactly like the isometry cube. So that means that that you can go to any point and you cannot see the difference on the manifold, and you can turn in any direction at any point and you cannot see the difference. And this is perhaps something that we can make sense of for a sub-Riemannian manifold. That's why I'm introducing it. Note that these have some specific properties. So, for example, for model spaces, being flat means that your homology is holonomy is trivial. Sorry, while your holonomy is equal to SON. Otherwise, if you're non-flat, so the maximal possible, and only the three-dimensional, only the flat case is a Lie group, with the exception of some shenanigans going on with three-dimensional spheres. But three-dimensional spheres don't have some isometries that are not Lie group automorphisms, which is different from the case of the flat space. And we're going to show that basically some of the same properties can show up for sub-Riemannian model spaces. This ends the first part, which summarized the Riemannian case. And now we can take, I give the word over to me from yesterday, who will explain you the rest on sub-Riemannian geometry. So, quick introduction to sub-Riemannian manifolds. So, sub-Riemannian manifolds, we have now the same kind of setup, but the only difference is that we have a subbundle H of the tangent bundle where the inner product is defined. So, unlike having it on all of the manifold, we now only have it on a subbundle. In general, if we just pick any sort of random subbundle, this does not give us any sort of meaningful geometry. So the typical assumption is that we assume that this subbundle we have is bracket generating, meaning that we can iterate all vector fields with values in this H and eventually get the whole tangent bundle. Another way of thinking about it is that you can take all derivatives in the direction of H, and then you can combine them into making any sort of first order derivative you want. If you have this condition, then any pair of points in your manifold can be connected with a curve that is only tangent to these directions, H. And this is good because we only have a metric on the subbundle. So this is the only place where we can talk about how long things are. So that means that we can define a metric by saying that by taking a pair of points, picking a curve that's horizontal. In this sense, it means tangent to this H, and then taking the infimum of all of these curves. So we can make a similar setup in the setting. So a typical example is the Heisenberg group. This is the simplest non-trivial case where you have R3, and then we have the following vector fields A1 and A2. Together, their brackets form the missing direction, which is going upwards. And in otherwise, going in either the X or the Y directions forces you to either go to change a little bit in the Z directions as well. So this this metric, then you get a metric on the space. This is not equivalent to Lipschitz equivalent to any Riemannian metric. So in the sense that X and Y as coordinate functions will be of order 1, while the third coordinate will be of order 2. This will have Hausdorff dimension 4. And this is some idea of what it looks like. So this is an intersection of the horizontal bundle in the XY plane. This is what a ball looks like in this geometry. So it looks like kind of sort of apple where you have two singularities on the top and the bottom, because it's so much harder to go up than to go to other directions. This is what a geodesic looks like. So it, in a certain, someone put it like this, that you can move around in the space, but you cannot take the elevator. You have to take the stairs, right? So you can go around and you essentially you generate area as you move around, and this area will take you up and down. And though it will not be the same Lipschitz equivalent to any Riemannian metric, it will give you the same topology. So we have the same open sets with respect to this metric. The way you can also, so this this space, the Heisenberg group, you can consider this as some sort of Lie group with which is nilpotent. So if I consider A1, A2, and A3 as a Lie algebra, then okay, the brackets of A1 and A2, it gives you A3. Brackets with A3 with both A1 and A2 gives you 0. So this is a nilpotent Lie algebra. So you can consider this as being some sort of left invariant structure on a nilpotent Lie group. That is why it's called the Heisenberg group. And this is general what all sub-Riemannian manifolds look like if you zoom in. So all the Riemannian manifolds, they don't only look like Rn topologically when you zoom in. Any Riemannian manifold, if you stretch them out, if you multiply with a constant, then eventually all of the curvature will disappear and you will become flat. That is why it looks like we're living on a flat Earth locally, because the Earth is so huge compared to us. And for sub-Riemannian manifolds, you will always end up looking like what is called a Carnot group, which is a nilpotent group, where the first layer combined with one of the other layers always generate the next layer. And then you can, since it's a nilpotent group, you can get a Lie group by just using the Baker-Campbell-Hausdorff formula. And you get a simply connected group, and then you can get a sub-Riemannian structure by just doing left translation of the first layer with its inner product. And so these are what are the flat spaces. This is what all sub-Riemannian spaces look like when you look very close. So the question is now, what are the analogs of the sphere and the hyperbolic space? So these are the analogs of Rn. It's too bad that there is a whole class of these, so they are own separate universe. But what is the analog of spheres? What is the analog of hyperbolic space? What is the analog of curvature? So let's try to find some way of talking about curvature of the spaces. And the problem is that we have these three conditions that are listed here is what we would very much like to do in order to do exactly the same as Riemannian manifolds, but they are incompatible. So I should probably make this incompatible bold. So you cannot have some sort of connection that is compatible with your sub-Riemannian structure that is torsion free and which gives you a bracket generating, or where H is bracket generating. This is impossible. So we have no torsion-free compatible connections in the general case. So we need to find some other source for idea of what curvature will mean. Oh yeah, this is probably, I should probably have put this earlier with the definition, but okay, why do you want to care about sub-Riemannian structure? Well, at all. Well, they show up in control theory. They are fun as metric spaces, show up in gauge theory and image processing, and recently also on statistics on manifolds with Summer. If you care about second order operators that are not elliptic, but so that show up like this where these coefficients A or J are only are only positive definite, then this corresponds to something in a sub-Riemannian setting. This can also be if you look at the corresponding like stochastic processes with these LSS generators. Yeah, and I put a bunch of references, but I'm already spending way too much time. So just ask me for the slides if you want the references. But okay, so let's talk about now some results before we finish. So let's first ask how can we look at what is a model in this sort space. So we, as I said before, we don't necessarily have the Levi-Civita connection. We don't have these, don't know what the sectional curvature is, but we do know what an isometry is, because model spaces was also the space that had a lot of isometries. So let's start with that from that point of view. So a isometry will then be a homeomorphism that also preserves the distance. And if you look at how the rank is generated and how the vector fields in this H generate the entire tangent bundle, if they do that in a sort of regular way where they generate the same amount of space every time at every point, then it's known that the isometries are smooth, and that it's sufficient to require the differential maps at H, and that it works on the isometry on each fiber as an isometry in each fiber. So this question is still open, whether or not isometries are smooth when this growth conditions of the brackets here don't hold. So this is still an open question in this geometry. One way to look at it is to introduce a model space in the sense of isometries by saying that that something is a model space if it's satisfied the previous condition. So that you have a sub-Riemannian manifold where H is bracket generating, and then whenever you take some sort of linear isometry between 2 points and in 2 different directions, then you can integrate it into a diffeomorphism, a global isometry. So this condition you can set up. It doesn't require any sort of connection, and then you can see, okay, what kind of spaces exists with this property. So so we have the definition of the Levi-Civita connection as the one that was compatible and that was torsion free, but we also have that the Levi-Civita connection is invariant under isometries. And if you are on the sphere and on the hyperbolic space, then this invariance under isometry is enough to actually determine the connection uniquely. You have enough isometries to do that. So we have a similar phenomenon as well in the sub-Riemannian case. We have something called a partial connection in the setting, meaning that you can only do derivatives in one direction. So if you are a sub-Riemannian model space, if you have a lot of isometries, then you have a unique, then all of these isometries introduce a unique partial connection, meaning that, let's see, did I not include the slide that has partial connections? Oh yeah, here is the definition of partial connections. So let's do that first. Sorry, I switched the slides order. So if you have partial connection is in the direction of H, means that you only have derivatives in the direction of H. So it's just like an affine connection, but with the derivatives only defined somewhere. And so in the setting, this connection is partial. This is not because the y is in H, it's because the x is only in H. That's what makes it partial. So you can define partial connections on other vector bundles as well. And if you have enough isometries, then I showed that there is a unique one that is compatible with this, with all the isometries. Now, why does this help to have a partial connection? Well, in an unrelated work with some other people, I showed that you can define, there is a way you can define and compute holonomies of such partial connections. So you can do loops that go along H, and you can define groups. So that means that canonically to these sort of structures, we now have some associated holonomy groups. Let's see, yeah. And this, let's see, where is the general result? Did I skip that? No, I just deleted one slide too many. But anyway, yeah, so I'll just say that orally. So, and what I'm able to compute is that just like in the Riemannian case, if you are a sub-Riemannian model space, then either your holonomy is 0 and you are a Lie group like Rn, or in the other case, your holonomy is SON. But then you can take your what's called the orthonormal frame bundle and make that a sub-Riemannian geometry, which is flat. So sub-Riemannian manifolds that are model spaces are either Lie groups with a lot of isometries, or there's some SON quotient of a Lie group with a lot of isometries. So let's look at two examples. So one example is what are all the model spaces of step 2. That means that you take your H and then you take brackets of all vector fields in H with itself, and then you're done. What are all the model spaces that fit this description? Well, if you zoom in on any such model space, then they will all have to have the maximal growth vector, meaning that they will all be they will all look like the free group on n generators with 2 steps. And if you are some sort of model space in step 2, then either you are this free group, or you have the curved version where you are either the frame bundle essentially of the sphere or the frame bundle of the hyperbolic space. So you are either SON plus 1 or SON 1 with sub-Riemannian structure defined by the Levi-Civita connection. So this, if you're used to seeing the sphere as the quotient of SON plus 1 divided by SON, there is a unique way to pick a complement there. And that is the one you use for the horizontal bundle. So either you're this case you're either this frame bundle case for the sphere or for the hyperbolic space. So in particular, these spaces are curved, but they are not curved in the same way as Riemannian spaces, because they all have trivial holonomy in a certain setting. They are all Lie groups. Next, let's do another lower dimensional case, which is called Cartan 235, which is where the flat model is given by this space here, where you have a Lie group of step 3. So you have, if you have an nilpotent group where if you take any triple bracket, it will disappear. Any bracket larger than 3 will disappear. Sorry. So this one should be a set, not a Y. But anyway, you have a bracket of x1 and x2 gives you z, not y, and x1 with z gives you y. That we then, the way this first appeared is you can think of the following setting. You roll a ball on the table. Now, where you are on the ball, that's 2 coordinates. Where you're on the table, that's also 2 coordinates. And then you can twist the ball like this. That's a third, that's a 5th coordinate. So that's a 5-dimensional system. And then you can say, well, I will not allow the ball to slide. I will not be able to just slide it, and I will not be able to just twist the ball in place. Whenever I want to turn or to move on the ball, I also have to move on the table. Then I have 5 coordinates, 2 ways of moving, because I have to move with the ball no matter what, or on the table no matter what. And so this gives us a sub-Riemannian manifold, and then doing sort of zooming in on that gives us this system here. And then what you can do is I took this system, which was known from Cartan, and I move it. I made a n-dimensional version of this, where you have the first layer is, and the third layer is just Rn. The second layer should be SON. Well, it's and then the first 2, they do this commutator thing to give you something in SON. And then what you do is you evaluate that matrix here. That gives you another step to the potent group that generalizes these sort of things. And so I found in this setting that there are exactly 2 parameters describing all models in this sort of setting. So it starts by 2, 3, 5, and then you can go to as many dimensions as you want. So here there are 2 curvatures, not 1, and they scale differently depending on how you map. And a subset of these corresponds to exactly these sort of rolling. And it was sort of conventional wisdom before I did that all these models, all these rolling spaces were exactly all the models that existed. And I showed that there was sort of, that these only contained in like a subspace of all of these sort of things. So that's the second sort of cases. And then most cases, it's not known what the model spaces are. So I did some more with my students, where we look at that, some lower dimensional models, and showed that different versions of G2 shows up there, the exceptional Lie group. But in general, very little is known about what are these sort of spaces. Now, let's go back to differences between sub-Riemannian manifolds. So another thing we want to do is there should be a way to look at the difference between sub-Riemannian manifolds, at least to see if they're flat. If you just give me something in coordinates, can you determine if they are actually flat or not, if they're actually this flat space? So there exists no results in sub-Riemannian geometry of how you would see if something is flat or not up until 2008. And then in 2008, Tori Morimoto gave a way to introduce something that was similar to the Levi-Civita connection for sub-Riemannian structures. And no one understood it and just ignored it until I started looking at this sort of recently, and how, because it was all written in terms of Cartan geometry. No one knew, other people knew Cartan geometry. So I translated it into this following thing here. So even though you don't have any compatible connections that are torsion-free, you do have a unique choice of connections in this setting, but only if your manifold looks the same when you zoom in. So so it's very difficult to understand. So essentially, curvature tells you how far your manifold is from being Rn. So if you have a geometric structure where zooming in, it looks different everywhere, then it's very difficult to describe what it means to be different from your tangent. So the underlying assumption is that zooming in everywhere, we need to be the same. And then there exists actually a unique connection which satisfies all of these terrible properties, which turns out to become Levi-Civita once you reduce it to the Riemannian case, but in general it's very complicated. This means that you can, in a certain sense, write out the what it means for something to be flat in a canonical way. So I'll just skip to the last slide because I think I've been talking way too much in these things. So since I've just been talking about this 2, 3, 5, let's see. Yes, here. Let's talk about that. So here is what flatness theorem looks like for 2, 3, 5 manifolds. It's extremely, extremely complicated, but it means that it's like exists, and you can take this technique and apply it to any sort of setting you want. So assume that you have a Riemannian manifold. Now I called it E instead of H. I'm sorry for that, but okay, this time my horizontal bond is called E, where it's like, okay, it's two-dimensional. If you take one bracket, you get a third vector field. If you take another bracket, you get 2 more vector fields, like before. Then you pick, and you have no idea if it's isomorphic to this flat thing that we showed. Then you pick any 2 vector fields. Then you take that it gives you an orthonormal basis. Then you pick the bracket and these 2 brackets, and then you compute all of their structure coefficients. Then you can do this horrible computation here, defining set and y1 and y2. But the good thing is that in the end of the day, if you manage to go through that, no matter which vector field you picked in the beginning, the set and the span of the set and the y1 and the y2, they become independent of the basis. So now you have a canonical way of picking these sort of complements. And then finally, you can define, you can extend your connection here to a connection that makes, you can take all of these to become a new orthonormal basis. You extend it, you use its Levi-Civita connection to define another very complicated connection, but it turns out that this connection is independent of choice of also x and y. And now you can check if it's flat by computing the curvature. And if the curvature vanishes and the torsion is as small as it could be, which is that it's just given by these internal brackets going forward, then you are flat. So you can then, and then these vector fields that you have, you can make them into left invariant vector fields. So that means that there is using some complicated tool, it is actually possible to look at the difference between sub-Riemannian manifolds. And I think I kept you long enough. Thank you for very much for listening to me.
Thank you very much, Adam. So, any questions?
You talked at some point about its use in control.
Yeah.
Do you have a couple of examples where
So,
from the board?
yeah, so so it shows up in control theory whenever the space of control is smaller than the space where if you have fewer controls compared to your space. That's essentially it. So if you have the same amount of controls, you can make a Riemannian setting, or usually it depends, of course, what your cost function is. But say you have a sort of quadratic cost function, yeah.
No, that I get, but there is a technical condition to make it interesting.
Yeah.
Say something.
Yeah. So this. So in terms of control theory, this is a sufficient condition to make it completely controllable in this sort of setting. So you can have weaker condition where you also have controllability, but these spaces look very bad, and you end up with so this is the natural good condition if you want also controllability locally. I mean, being able to go to any directions, right? You can have global controllability where you go somewhere else and then turn there, and then you're able to move. But this is not very good if you want to do computations globally. So this condition of generating things, this is also the natural conditions in control theory for complete controllability. Yeah. So the ESX control theory example you can have is like driving. So driving, you have two controls. You have your gas pedal, you have your brake, but brake is just minus gas pedal. So that's one control. And then you have your steering wheel, right? And then your car has 3 parameters, because it is where it is and then which direction it's facing. And then you can change that with your steering wheel and your gas pedal. And in this setting, you are able, because the vector field of the steering wheel and the gas pedal, they actually make the third direction.
Yeah. Okay.
You can go anywhere you want with your car. So that's the typical example in control theory relating to this. Yeah.
You had the slide with the D groups and then the orthogonal frame bundle.
Yeah.
And like you said, that sometimes you need to have the orthogonal frame bundle. But can you maybe just put a few more words on the connection between like SON there and the orthogonal frame bundle?
Let's see. Let's go back. Okay. Yes. So yes. So let's do it for the sphere. It's the same as in the hyperbolic space if you think of it as the sphere in Minkowski space. So okay, you have the sphere, and then if you have which is inside of Rn+1, and then you can act on it with an orthogonal matrix in Rn+1, and then preserves our length, so it preserves the sphere. But if you have a tangent vector at a point in the sphere, you can also move any tangent vector to where you want with the matrix SON. Now, now take a tangent vector on the sphere, and then a curve on the manifold, and take a curve on the sphere. And then from your starting point to ending point, you parallel transport a frame along this curve, right? So then what you can do is you can write that your curve along with your parallel transport as a curve in SON+1. You essentially what you do is you take the position on the sphere plus your frame, and which is then taken to a position on the sphere plus a frame. So it's a basis of Rn+1 to a basis of Rn+1. Then you see, okay, what matrix in SON do I need to move it from here to there? Okay, so now you have a curve inside of SON plus 1, which is made in a specific way. It's made by parallel transport. Now you can take the derivative of all of these curves, which gives you some of the derivatives that is in SON plus 1, but it doesn't give you all of them, because in order to do parallel transport, you actually need to move on the sphere, right? So you don't get any of the ones where you just rotate in place. And so you get, again, then an H on the top manifold, so a subbundle, which is transfers to all the rotation. And so in this setting, the model spaces is the S for the sphere is the SON plus 1, where the H is the subbundle that is transfers to the rotation that comes from the Levi-Civita connection downstairs. And there exists a similar setting for general Riemannian model space, where you can, if you have a model space where your holonomy is not trivial, then you can do the same trick. You can go to the orthonormal frames and make a horizontal bundle by saying, okay, it's the derivative of all parallel frames. And then you get a model space on the top, which is also a Lie group. So in this sort of setting.
And what would the group be in that? Would the group then be specific to the model space that you?
Yes, so the group will then be specific to a model space.
But larger than,
yeah,
like the n plus 1 here. So like something at X in the model space, and then you enlarge it to have the frame component.
Yeah. So that means that if you want to show something on the sub-Riemannian model space, it's usually sufficient to consider space just Lie groups, because the other ones are just SON quotients of Lie groups. And this works because like in the Riemannian setting, once I go from here to here, I'm outside of the Riemannian setting. Whereas for the sub-Riemannian setting, I can always also look. I can go an orthonormal frame bundle of a sub-Riemannian manifold can still be considered as a sub-Riemannian manifold. So yeah. That was a helpful answer.
Definitely. More questions? Okay, let's thank Alan again. And as you know, Alan